Alright, everyone, welcome back, and we are at it again with another episode of From the Rails Up. This time it's all about traction motors. In the last video, we talked about brake rigging, which is what makes us stop. This time we're talking about traction motors, which is what makes us go. And this is going to be a pretty long one, so brace yourselves. The list of topics I'd like to include today includes the parts of a traction motor and what they do, how we assemble combos, some of the lubrication and servicing requirements of traction motors, the different gear ratios that get used for different classes of service. Then we're going to get into a little bit of component theory and talk about how traction motors work and how we switch direction and how we set things up for dynamic braking and stuff like that. And then while we're talking about component theory, I'm also going to mention why DC? Why do we use DC traction motors, especially considering more modern locomotives more modern locomotives use AC traction motors. So why do these old ones still use DC? And then before we close out, I also have a couple pictures of some catastrophic failures I got that I think you guys will like to see. So with all that out of the way, let's get right into it. Alright, so traction motor parts. What you're looking at here is actually a 3D model of a traction motor that I made. Before we even really get started, I'd like to mention that this model is actually incomplete. Even with all of this, there's still some pieces that are missing, and there's still some stuff that I'm going to kind of hand wave away because I haven't had it apart enough to be able to tell you exactly what everything looks like. Looking at this picture, we're going to ignore some parts now that are going to come into play later whenever we actually talk about combos, so that'll get rid of some of this stuff. And so that leaves us with this, and this is what we're going to talk about for now. So the first thing we have is this big green block here, and this is the motor frame. The motor frame supports everything predictably, and it also is enclosed on one end, and that actually makes it act as kind of an air duct to help direct the cooling air around the electrical components inside the motor. And it comes equipped with these blue covers that can be removed, and it allows access to the inside of the motor to help perform maintenance or troubleshoot things and the like. The next thing we have here is this armature support bearing. All this really is here for, this is one of those things I haven't had apart. All this is really here for is it supports this end of the armature and lets everything spin freely. The next thing down the line on the model here is the A-leads. And these A-leads feed power to the armature, and also connected to them are these interpoles here. These interpoles, as well as the main poles, consist of a stack of iron laminations to reduce eddy current losses, just like in any other electric motor. But you have this stack of iron laminations that makes a core, and then you have a coil of wire going around it. These are called interpoles, and the interpoles help the electrical characteristics of the motor. It helps ensure proper commutation, which we'll talk about a little bit here when we get to the armature, which is actually next. The armature here is what's powered by the A-leads, and in a sentence, you put electricity in the motor and you get torque out, and that's how we move down the rail. I mentioned commutation just a second ago, and what commutation is as this armature turns, there's a series of bars, which I'll show you in a minute. It's called a commutator because if you know what a commute means, it's where you move from one place to another. Well, the commutator makes it so that the current flowing through the armature moves from one spot to the next down the line as the armature rotates. And that's actually what those interpoles are there for, because as this armature spins, it can distort the magnetic field we have inside and cause issues, so we put these interpoles in to help stop the motor from flashing over. Then we also have, on the other side of the armature, we have the F-leads, which these are the main field windings. These are the bigger poles. These are the main ones that actually provide the torque to actually turn the motor. Then we have another armature support bearing past that, and this one, obviously the housing for it is a little bit bigger than the other one. That's actually because the way that this motor would be assembled is you bolt the one armature support bearing in, and you can put all the field coils and all the all the interpole coils and all that stuff in. Then you can slide the entire armature down in through this side, and then you can put this bearing on the outside, and that's how the inside of the motor is actually assembled. Then the last component we have out here on the end is the pinion gear. And this pinion gear is what mates or meshes with the bull gear that we talked about on the wheel set. And so when this pinion turns, that's what actually applies the torque to the wheel set. Now, like I mentioned, some of this stuff I kind of hand-waved away a little bit, so I'll zoom in specifically on these parts here on the A-leads. These are called brush holders, and I didn't really model them the greatest because I haven't had a ton of them apart, so let's look at some actual pictures of one of these. So this here is a brush holder, and you can see it's made out of glass, and we have these two red, I'm going to say prongs, I don't really know what the technical word is for them. They stick up, and they're wrapped in insulating material, and then these are bolted into the traction motor frame. So these brush holders can actually be adjusted to get the proper clearance from the motor commutator. The brush holders, predictably, hold the traction motor brushes, and they are held down by these gray hammers here. These hammers are spring-loaded, so whenever you put a brush in, these hammers will put a little bit of pressure on it to keep it in contact as things move and shift and rotate. Now, to get the brush in or out, there's actually a little tab that I'll show you back in here behind these hammers to where you can lift the hammer up off the brush and slide it down, and it actually locks the hammer in a raised position, so that way you can pull the old brush out and put the new one in. Now, what's a brush look like? I've talked about them. Well, this is a picture of what this all looks like when it's actually put together. And here you can see we have these three brushes, and these are just blocks of carbon. I think they're just graphite. And they have these little lead wires come off of them that bolt to the brush holder, because the brush holder is where they actually get their current supply from. So whenever you change these brushes out, you actually have to unbolt them, pull the old one out, and then bolt the new ones in to ensure you have good connectivity. And you can pull the hammers back out, and they'll press down on the top of the brush just like this shows, and then that pushes them against the commutator. And here you can actually see what the commutator looks like. You got a bunch of copper bars, so as the armature rotates, the brush makes contact with one bar, then the next bar, then the next bar, and so on and so forth down the line. So that keeps the magnetic field of the armature in a good spot to get a lot of torque out of it. And then while I'm in here and this motor has the cover off of it, I'll show you a picture of what the rest of the armature as well as the main and inner poles actually look like when you look in at the motor from. It's kind of a weird angle that you don't get to see when it's actually inside the truck frame. So, here's a picture. Here you can see you got the two main poles on the top of the motor and the front of the motor. Then we have an inner pole here, and there's another one over here. And then, obviously, the other side of the motor, there's two more main poles and two more inner poles. That's a little picture of what some of the guts of a traction motor look like. One last thing I do want to mention while I'm out here is we have, if you go to this picture, which is just a whole motor, you can see we have 4 leads. And those leads are numbered from left to right, or not numbered, but they're named from left to right. A, AA, F, FF. A for armature, F for field. So the A and AA leads both feed power to the armature, like we talked about. And then the F and FF leads both feed power to the field. And these do matter if you ever have to take one of these apart. It's important that A and AA and AA and so on, that they don't end up mixed up. Because if you do mix them up, then bad things can happen. Keep that in mind as we go forward. Yeah, that's pretty much all the parts of a traction motor. That honestly didn't take me quite as long to get through as I thought it would, so I guess that's nice. Now we're going to move on from here to actually assembling a combo. Alright, so on to talking about combos. Before we talk about assembling them, I'll actually blitz through some pictures of some combo parts, some actual parts, because I don't have these necessarily modeled 100% faithfully, because it's honestly been a while since I've actually had a traction motor apart. So we'll blitz through some quick pictures of some actual parts, and then go through the rough idea how to assemble them. So starting with combo parts, you're going to have the support bearings, the support bearing caps, there's an axle shield, the support bearing caps have wicks in them for lubrication. You have the gear case, and you'll often hear me refer to that as a crater pan, because that's what our truck shop foreman calls them. And then we have a bunch of seals between the pan halves, inner and outer pan seal, a pinion seal, and then a dust seal on the other side of the axle. First things first, talk about support bearings. I'll throw a picture of one up here for you. We have a motor half and a cap half of a support bearing. The way you can tell them apart is the motor half will be solid and the cap half will have a big slot in it, and that slot is for the wick. If you look at the outside faces of the support bearing halves, you can see they have these wicks on them. These wicks are also there for lubrication, and they provide lubrication to the hub of the wheel as it shifts back and forth during some kind of movement. And if you look at a picture of an actual support bearing cap, you can see it has a slot for the wick, and they also are hollow on the inside, and they hold a reservoir of oil for lubrication. And then you can also see that one of these support bearings has this arm sticking off of it, and that's what supports the crater pan. And then also, whenever you assemble these, they have a set of shims that go between the support bearing cap and the motor whenever you bolt everything together. Just wanted to mention that. We also have the axle shield. There's not really anything special about it. It's just there to cover the axle and to keep dirt and grit out of the support bearings so we don't wear things out faster than we need to. The next thing we have is wicks, and I'll throw up a picture of some wicks we have. They are hanging out in a bath of oil to soak, so that way they're pre-lubricated, if you will, for when they get assembled into a combo. These wicks, as I mentioned, sit inside the support bearing caps, and the support bearing caps are full of oil, so the end of the wick actually sticks down into that bath of oil, and so just like a wick in an old oil burning lamp, it wicks that oil up, and then as the axle turns, that oil sticks to the axle and gets spread throughout the bearing to lubricate everything. And then the next thing we have is the gear case, or the crater pan. Crater pan comes in two halves, an upper and a lower, and the top half is going to have this slot in it where the bottom half mates into it, and that slot has a bunch of seals that go in there, which are the pan half seals we'll talk about in a minute. Some of these gear cases are lubricated with oil, and some of them are lubricated with grease. We'll talk about that in a little bit. But to know the difference, an oil pan on the bottom half will have either a drain plug or a snap cap. A grease pan will have on both halves a spring-loaded cap that'll look something like this. This one's dirty as all get out, but it'll look something like that. If it has one of those on both halves, that is a grease pan. And then many, although not all, of these crater pans also have overflows in them, so if you put too much oil or too much grease in it, it can actually run out onto the ground. So you don't want to overfill them, but you do want them full. And as far as seals, these are the pan half seals. They go down in between the pan halves, and they get silicone and everything whenever they go together. We have the inside crater pan seal and the outside crater pan seal. They look slightly different, and the inside seal and the dust seal, actually, for that matter, both have these little bumps that stick out, and there's actually matching holes drilled into the support bearings that hold these seals in place so they don't rotate. We also have the pinion seal, and the pinion seal comes in two halves, and those two halves will look just like this. I know some of these pictures got washed out. I apologize for that. I'm not a great photographer, but the pinion seal comes in two halves, one in each half of the crater pan. Then when you bolt it together, that's what makes the seal around the traction motor. And then we also have this dust seal, which is on the other side of the axle. And just like the axle shield, that dust shield is there to try and keep grit out of the support bearings. So that was a pretty quick crash course, blitzing through some of the parts that I ignored when talking about the traction motor. So let's go to a rough overview of how we actually put one of these together. Normally, we'll stand it up on its end so that the bearing end is pointed straight up. So you're going to have to picture all this sitting like that. But we'll put the motor side support bearing halves in, and they'll have their wicks and everything all pre-assembled. Then we'll set the axle in. Then we'll put the cap side support bearings on and the axle shield. Then we'll put the shims and the bearing caps on and get ready to tighten everything down. Now these bearing caps, whenever you tighten them down, you actually have some funky stuff you have to do, because you want to make sure whenever you bolt this stuff down that the support bearings are lined up correctly. So what you end up doing, and it's a real treat, it takes two guys to do this. You'll have one guy with two pry bars. He'll use one pry bar to pry the axle away from whatever side you're tightening. And then he'll use the other pry bar to pry the bearing cap you're tightening out against the wheel hub. That way you can make sure everything lines up flush and nice and pretty and goes together right. And so you have one guy holding all that, and then the other guy will take an impact and tighten these. And if I remember the torque spec correctly, they go to something obscene like, I think it's like 12 or 1,400 foot-pounds. Don't quote me on that. I'd have to actually go look. But yeah, you tighten the ever-living daylights out of them. And then whenever you get to one side done, then you got to go do the other side. And there is one side that you're supposed to do first, I think, and I can't for the life of me remember, or it might not matter. But yeah, those are a treat to do them. It takes two guys and a good bit of elbow grease. Then the next thing we'll put in is the traction motor wicks. These have been soaking in a bath of oil like I mentioned, so they should have some oil in them to lubricate everything. Then you will take the dust seal, the inner and outer crater pan seals, the pan half seals, which I don't have modeled, and the pinion seals, and all assemble them all together into the crater pan. And then the last thing we'll do is a lot of this stuff gets siliconed as it goes together too. I forgot to mention until now. Sorry. You put all the seals in the pan halves, and then you bolt everything together. And some of these things you got to make sure they line up. But yeah, you bolt everything together with the pan halves. There's different ways that these pans can be attached. Some railroads use huck bolts. Some of them have a special type of bolt and clamp that gets used. Huck bolts tend to be more reliable, but you also need specialty equipment to put them on and take them off. There's ups and downsides to everything. And then once you get the pan halves bolted together and you get everything assembled, then the last thing you're going to do is actually test run the motor. We have a welder that we can use for it. You hook it up, and all it does is just shoot electricity through the motor. And because it's sitting out and it's not, actually under a locomotive, it doesn't take much to get everything to turn. And as you do that, you want to listen, make sure you don't hear anything scraping or grinding or any weird chattering from the gears or anything that's kind of suspicious of something being wrong. That way whenever you put the thing in that it's going to perform and not, destroy itself. So that's a quick synopsis, brief overview of what it takes to get a traction motor combo put together. And I'll also mention a little bit here. We'll talk more about this, and it should be the next video on truck frames. But I'll mention here a little bit too that these combos can actually be changed if you have a drop table or something like that without removing the truck from the locomotive. It's kind of neat. So these traction motors are actually suspended on the axle by your support bearings, and then the other end is suspended by something called the nose suspension, which is in the truck frame. That nose suspension is there because as the motor tries to turn, which is easier to do, move an entire train or to lift this little 5 or 6 ton motor. It's going to try and move the motor. So it's going to, whenever it tries to turn the wheel, the pinion on the motor is going to try and walk around the axle, and that's not great. You want to absorb that force, but you also don't want to be slamming stuff back and forth. So they put a spring pack in there, which will look something like this, that holds up the one end of the motor. Now, to get that motor out, provided it's in a friendly place for you on the truck, you can actually block the truck frame. You can take 2 bolts out and you can drop this thing out on each side. This is called the pedestal tie bar. And if you have single shoe brake rigging, that's all you have to take out. But if you have class brake rigging, now you have to take out the brake straps too in order to get this down out of here. Remember when I mentioned that class brakes are kind of not preferred because they're a pain in the butt for maintenance? Yeah, this is one of the things. Brake rigging almost never wants to come apart. And anytime you got to drop a combo out and you have class brake rigging, you have to frickin' take the brake straps down. And it's a pain in the butt and a bunch of extra work. So with the single shoe brakes, all you got to do is pull the pin out of the slack adjuster. Then you can just drop the pedestal tie bars, and then you can actually lower the motor and it'll pivot off of that nose suspension, and then it can be dropped out without having to remove the truck. It's a pretty neat little thing that we do. I don't have a ton of pictures. Hopefully I can actually put like an animation of that together in the next video whenever we get to truck frames, but I figured I'd mention it here because it was kind of neat. It does act as a bit of a segue into our next section, which is on lubrication and maintenance anyway, so let's talk about that. Alright, lubrication and servicing of traction motors. As usual, whenever talking about maintenance stuff on the railroad, the FRA has something to say about it, although in this case there actually isn't that much. The only part that actually deals with anything is 49 CFR Part 229.91, which deals with motors and generators. So we'll blitz through that relatively quickly because, like I said, there ain't much to it. And we'll cover some other general inspection items there. We're also going to go through support bearings and journal boxes, crater pans and the gears inside of them, brushes and brush holders, as well as the commutator. And lastly, we have leads and cables on the outside of the traction motor. So a small amount of your inspection items stem from 49 CFR 229.91. It basically states that a motor or generator may not have any of the following conditions. May not A, be shorted or grounded, B, throw solder excessively, C, show evidence of coming apart, D, have an overheated support bearing, or E, have an excessive accumulation of oil. Shorting or grounding of a motor can be checked with a device called a megometer. What a megometer does is takes a voltage and it steps it up to something stupid high. I think the one we have goes up to 5,000 volts, and it flashes that into the system and it looks at how much current that's able to push. That's a way for checking insulation in high voltage circuits. It's also called a high potential tester. Throwing solder has to do with arcing and flashing inside the motor because arcs get really hot and they can melt things, and one of the first things to melt is solder, and it'll fling it out on the end of the motor, and you'll see usually they look like little BBs. They cannot show evidence of coming apart. That really has to do with, bearings, cracks, bolts being loose, those types of things. You don't want to see an overheated support bearing, which usually there will be more signs than a heat signature because these motors tend to have pretty thick paint on them and a lot of dirt. So you don't really see a heat signature, but you'll usually know if the support bearing's bad. And motors also aren't allowed to have an excessive accumulation of oil. Now that accumulation of oil is, in a lot of cases, going to come from the car body above the truck. It'll leak down and drip onto the traction motor. So they just can't be, completely covered and running in oil. A little bit here or there isn't a big deal, but you don't want a ton of it. Other things that should be checked whenever you're looking at a traction motor, you want to check condition of things like lead clamps, the grommets that the leads go through. You want to check the snap caps, the cooling air duct to make sure that's in decent condition. And you want to check any seals you see, your crater pan seals, your pinion seal, and the traction motor covers. And those covers actually should also have gaskets under them, because if there's not a gasket there, your cooling air can basically bypass the motor. It'll come down the duct and out the cover instead of actually going through the motor. So that kind of covers your general first look at kind of things. When it comes to support bearings and journal boxes, these are both lubricated with the same oil. It's called car oil or journal oil, and I would suspect that that term actually stems from back when we used plain bearings or friction bearings. This was the same oil, I'm guessing, that got used to lubricate those bearings. So it's still being used to lubricate axles, just now we have roller bearings instead. Both usually have a snap cap where the oil is added. I'll point one out here because I've mentioned these a few times. I don't think I've ever actually showed one. Both the support bearings and journal boxes, if you look at the oil, you want to check for any signs of failure. Usually that'll be in the form of metal particles. If a bearing starts to fail, usually metal will start to flake off and get into the oil and start getting mixed up with it. So if you open one of these and you see metal particles, that's a pretty good sign that something is wrong. And in the event of support bearings, it usually doesn't end up in the bearing itself. Usually it'll end up accumulating in either the dust seal or the crater pan, depending on which bearing it is. Although more often than just occasionally, it's the crater pan bearing, because that's the one that has the bowl gear on it and sees the extra force. Speaking of crater pans, the next thing is the crater pans and the gears themselves. There's two basic types of lubrication that these use. They can either use oil or grease. The oil is a very heavyweight oil, and I'll throw a clip of it up here, some of that oil in a bag, and if I flip it over you can see just how frickin' long it takes for the bubble of air in that bag of oil to actually reach the top. It's very viscous oil, and it's because it's dealing with a lot of pressure. It's very sticky compared to most oils because we want it to stick to the gear and actually lubricate everything. Grease pans will contain what we call crater compound or crater grease, hence the nickname crater pans. And that also comes in bags, and they usually look like this. This is like an actual soft-ish kind of grease. Here's a video again. You can see, you can squeeze it, but it's not a liquid, it's an actual grease. And again, this is very sticky. And a lot of railroads seem to use this. We don't, just because it's a pain in the butt to deal with whenever you're actually assembling combos. A big thing that's nice about grease is that grease doesn't leak like oil does. But anyway, I digress. This grease is also very sticky because, again, we want to make sure that as the everything speeds up in there, you're going 60 mile an hour down the track. You don't want to fling all the lubrication out of your gears and burn things up. To check the lubrication level in these pans, usually an oil pan will have either a drain plug like a differential or a snap cap just like the support bearings and journal boxes, and you can pull that out and you can look in and check the fill level, and you can add oil through the plug, or usually there's another plug on the top half of the pan. You can open that one and add. I usually like to keep about 3.5-ish inches in the bottom of the pan. That's just a rule of thumb. Different railroads and different pans, I'm sure, have different numbers. Grease pans will typically have a spring-loaded cap, and that cap can be removed with a special tool to check the amount of lubrication that's in there. And those big caps are how you can add bags of grease or oil to the crater pan. And this is kind of hilarious to me, because the first time I found out about this, I assumed you would cut the bag and squeeze all the grease out of it. But no, the first time I saw this, it was a brand new combo we just rebuilt, and we were test running it, and before we set it down and put it back in, our truck shop foreman lubricated it, and all he did was just held up a bag of oil or a bag of grease over the gears while it's sitting there running and just dropped it in, and the motor just bogged down and chewed it up, and he dropped 3 or 4 of them in there. So yeah, those bags can just go in, plastic and all, and the gears are just om nom nom and chew the plastic up, and the lubrication does its job. Also, while you're in the pan and have everything off, you should be checking the gears inside for spalling damage, heat checks, cracks, excessive wear, if the teeth get worn down to a point or anything like that. You want to notice that because something is very wrong and we don't want to lose pulling power going down the rail. Jumping to the inside of the motor, we have brushes, brush holders, and internal cabling as well, and the commutator. The brushes should be checked for burn lead wires that go from the brush holder to the brush. You want to make sure the brush isn't cracked. You want to make sure they aren't broken. You want to check, make sure that they move freely up and down. And you also want to make sure that the brushes aren't too short. These brushes I'm showing you here have wear lines on them. As long as you can see that last wear line, as a rule of thumb, you should be fine. Different brushes, different manufacturers, different motors, different maintenance schedules, all will change how long exactly you're allowed to have that brush and it still be serviceable. But if I recall correctly, EMD says if there is at least an 1/8 of an inch gap between the hammer that holds the brush down and the bottom of the slot in the brush holder, that brush should perform for the next 92 days. In practice, I don't think we've ever let them get that short, but that's what EMD says. We usually change them out at about that last wear line. The brush holders themselves, you want to check them for spring tension. These hammers have a certain amount of spring tension on them. Now in practice, usually you don't get like an actual, scale out and check them, but usually by feel, if you have one that has almost no tension on it, or if you have one that's extremely hard to pull, something's probably wrong there. You also want to check the brush holders for melted spots that would indicate excessive arcing from the commutator or other brush holders to that brush holder, or from cabling or anything like that. And the last thing you want to check on the brush holders is the air gap, the distance between the bottom of the brush holder and the commutator. That gap should be even all the way across. It should be between, if I remember the spec right, it's 1/16 of an inch to 3/16 of an inch. Excessive air gap can cause the brushes to fail because this gap being small means that the brush is held very close down, whereas if you hold it farther up, it's a lot easier to break it. Just like how it's easier to break a longer stick by grabbing it at the ends than breaking a shorter stick. And these brushes are very delicate, so we want to make sure that they're held nice and close to the commutator. While you're inside the motor looking at the brush holders, you also want to check there's interior cabling, there's the field coils that we talked about earlier. You want to check the insulation on all those things, make sure you don't see anything cracked, make sure you don't see anything metal touching anything it shouldn't be, which will cause things to ground out. And you want to check the brackets and clamps that hold everything in, including the brush holders, and make sure that the bolts are tight and that stuff can't move. And the last thing we have inside the motor is the commutator itself. The commutator bars should be checked for signs of abnormal wear, like if it's grooved where the brushes are. You want to also look for conditions like copper drag, which is where a little bit of copper gets drug off the trailing edge of the bar and it can cause bars to short together if it's severe enough. There's also a defect called edge burning, and both of these can lead to improper commutation of the motor and can cause a flashover. Some of these commutator issues can actually be fixed by stoning the commutator. What stoning a commutator does is you take, it's literally a stone and it's abrasive, so you'll run the motor so it's sitting there spinning, and you'll run this stone back and forth across the commutator surface, and that'll smooth everything out. It'll take out any high or low bars. It smooths the surface so it's nice and square. It leaves a nice wear surface for your brushes to seat into. Now, particularly severe defects can't be fixed this way, but if you had a little bit of threading or a little bit of grooving, it can be dealt with by stoning and you should be all right. And then going back to the outside of the motor, the last item we really have to deal with are the traction motor leads and cables. The lead is on the traction motor side and the cable is on the locomotive side. They can be unhooked to allow you to remove the traction motor in the combo without having to actually pull a bunch of cabling out of the locomotive. And where they bolt up, these are called lugs. There's two basic styles of them. They are bolt-on and or glad hand lugs. Bolt-on lugs are what's pictured here. You have two holes, you run bolts through them, and there's a special nut that goes on the back side, and when you tighten everything down, it clamps the lugs together and ensures your electrical connection. Glad hand lugs, they work like your air hoses, where you hold them together and then you turn them, and as they pivot, they lock together to give you your electrical connection. Now, I say they work like air hoses, but don't let me make you think that they go together easily. More often than not, to get these together or apart, you have to wail on them with a hammer a little bit to get them to actually move. Other things you want to check about the cables, you want to check for, cracked insulation, cuts in the insulation, broken wires, signs of overheating. You want to check and make sure that they have lead boots. You don't see any, signs of overheating, cracks, wear out there. You want to make sure the lead boot is properly positioned. It's supposed to be at least 2 inches from the exposed metal on the lug. So you put the lead boot on, bolt the lug up, and then slide the lead boot up so ideally it's centered over that lug connection area, and that provides your insulation. In addition to your 4 main leads that we talked about, there is also a smaller ground strap that should be checked. You want to make sure it's connected tightly to the locomotive frame, and you also want to make sure that it's not broken. The insulation doesn't really matter on the ground strap because all this is here for is if something inside the motor arcs somewhere it's not supposed to, this will allow that current to flow back to the car body, and which will trip the ground relay and let the crew know that something is wrong. So the insulation doesn't really matter, but it does have to be on there tight and it can't be broken or else it doesn't work. If you are removing to replace a motor, you should label the cable connections on the locomotive end, which one goes to which, because sometimes it's not very obvious, and if you hook them up wrong, you can have a traction motor that doesn't work at all or one that loads backwards. Ask me how I know you can do that, because that was a fun day, let me tell you. But that is a fairly generalized overview of what you want to check when you're inspecting traction motors and as far as lubrication and servicing. So the next thing I would like to talk about is gear ratios and the different gear ratios that some of these traction motors have. Alright, so gear ratios. This seems like kind of an odd topic because diesel-electric locomotives don't have really a proper transmission. It's just a traction motor and then the axle. So there's no real transmission. You don't have gears to shift like you would in a car or truck, but there are different gear ratios that are available. So usually when you buy a traction motor, they will come with a pinion on it, and you can order which pinion it gets. And the pinion is held on with a specialty nut, and that nut, you can remove it and you can either pull the pinion off or you can cut the pinion into 2 or 3 pieces, and those 2 or 3 pieces will fall off. So my point here is the pinion can be removed. You can't really change the bull gear on the axle. You'd have to buy a different axle. But the ratio between the number of teeth on the pinion gear and the number of teeth on the bull gear determines a couple things. It determines how much tractive effort you can get out of that axle. The more aggressive the gear ratio, the more torque you can put on the axle. It will change the minimum speed you need for continuous drag and full horsepower. Because we'll get into that nuance way later on when we're talking about excitation. But there's a certain amount of speed a locomotive has to be going before it can actually put down its full horsepower to the rails. And the last thing that the gear ratio affects is the top speed of the locomotive. This is the other side. The more aggressive the gear ratio, the faster that armature has to spin in order to make a top speed. I'm not sure if it's limited based on how fast can we spin the armature before it starts to arc and do weird things electrically, or if it's more of a how fast can we spin the armature before it starts to fail mechanically. But either way, the more aggressive the gear ratio, you get more pulling power and a lower speed for full horsepower, but you have a lower top speed overall. So railroad for railroad, application for application, you will get different gear ratios for these traction motors depending on use case. Specifically talking with the old EMD D77 and 78 motors that I'm familiar with, there are 6 different gear ratios available ranging from 62 to 15 to 57 to 20. The 62 to 15 has a top speed of 65 miles per hour before you start to spin things too fast. For the 50-70 to 20 gear ratio, the top speed is listed as 95. Now that's a little talk about gear ratios. And the way you can tell what one you have, usually it doesn't say anything on the pinion, you just kind of have to tough it out and count the teeth on it. But usually if you look at the bull gear, and I'll throw a picture of one up here, usually somewhere on a bull gear, on a wheel set, there's a painted number on there that tells you how many teeth are on that bull gear. All of our EMD motors are set up for 62 to 15 gear ratios, so ours will all say 62. Different manufacturers use different gear ratios, like GE's are, I believe, 74 to 18. It's just different use case. There's more teeth and they're smaller, whereas the EMDs have they're 62 to 15, a little bit less teeth. So now we get to go on into the really fun stuff, and that is component theory, and you're going to get to watch me try and draw some prints in Photoshop. So have fun. Alright, now for the fun part, which is you guys getting to listen to me, someone who's not a physics major nor an electrical engineer, try and explain how an electric motor works. This should be fun. Before we get to that, though, I want to explain some symbols and show you what one of these would look like on a print. What you're looking at here is a simplified print of what a traction motor would look like. Now, these symbols, if they look a little funky to you, that's because they're different from ISO symbols, which is what literally everybody else uses and was what I was used to before I came into the industry. Enjoy that, you're just going to have to frickin' deal with it. At the top in the center we have a symbol and it's labeled main gen. Now typically they're actually alternators, but they'll just say main gen, or sometimes you'll see main alt, traction alt, but pretty much everyone I've ever seen still says main generator. And from your main gen you go over to your positive bus and negative bus. So all the positive connections that come out of the main gen come out of this positive bus. And all the negative connections that come out of the main gen come out of this negative bus. Again, this is simplified. There's other stuff going on, but you have your main gen, you have conductors to your buses. And if you look below, you can see this little circle with two kind of blocks sort of sticking out of it. That's your armature symbol. Any traction motor armature will look like that. And your armature are your A leads. So your A and AA leads are connected to your armature. And the fields look like this. They're depicted by 3 humps. And those are your traction motor fields. And those leads would be your F and FF leads. Anytime you see something like this on a print, it's representing motor fields. So that's a little crash course on what these print symbols are going to look like as we go forward. Now, the traction motors that we use in locomotives are all series wound motors. Now, what does series wound mean? A series wound motor is a motor in which the current flows through the armature and through the fields, all of it. All the current goes through the armature, all of it goes through the fields. This is different from a shunt motor, where instead of being in series, through the armature and then through the fields, it is in parallel. So it comes in, it forks, some of the current goes through the armature, some of the current goes through the fields. We do not use those for traction. And the main reason for that is a series wound motor, you can shove a bunch of current through it, and that gives you an insane amount of starting torque to get the motor to start rolling. And when you're trying to start, 20, 30, 40,000 tons of train, a lot of torque is exactly what you need to try and get things moving. So, knowing that these are series wound motors and we have to get current from the armature to the fields or fields to the armature, whenever we go to test these motors, remember I mentioned test running them before we actually put them in anything. So whenever we do that, we just simply connect the AA and F leads together. And I'll represent that here just by drawing a line. Usually we just bolt them together. Then we'll take a welder that's set up for this kind of application, and you can clip the positive lead on the A lead and the negative lead from the welder on the FF lead. And you turn the welder on, it'll put power through the motor and it'll turn the motor forward. And when I say forward, what I mean is it will turn the motor in such a way that the axle will drive in a direction that will pull the motor towards the support bearings, if that makes any sense. I consider the support bearings the front of the motor. So if you turn the wheel set in such a way that it pulls the motor towards the support bearings, that motor is turning forward. So if you put the positive lead on A and the negative lead on FF, the motor turns forward. So if you turn the welder off and flip them around so the positive lead's on FF and the negative lead's on A, turn the welder on, the motor will turn forward. This is a kind of confusing thing about traction motors because they're not permanent magnet motors. If this was a permanent magnet motor, that would have worked. This is not a permanent magnet motor. So how do we get reverse? Well, to get that, we have to change what leads are connected. So if instead of connecting the AA and F leads, we instead connected the AA and FF leads, and then we stick our positive on our A lead and our negative on our F lead, then we'll get a reverse rotation out of it. So why the heck do we need to do all that? Well, to explain that, I'm going to call on this simplified diagram I made in all of its beautiful asymmetric glory. It's simplified because we are completely ignoring interpoles. You don't need to worry about them for this. They're just there because the motor field flux gets distorted when you try and actually use it. So what you're looking at here is the traction motor from the commutator end. Am I making sense here? You're looking at the commutator inside the traction motor. This is opposite of where the pinion gear is. So the front of the motor is going to be where the support bearings are, which would be on your right. So if the motor's rotating forward, it will drive the ball gear in such a way to drag the wheel set and the motor to the right. Okay? Okay. So there is a rule for figuring out how a motor works, and that is Fleming's left-hand rule. So if you take your hand and you hold it out in a pose like this, where your index finger, middle finger, and thumb are all roughly perpendicular to each other, that's the left-hand rule. Your index finger represents the magnetic flux. Now, flux is just a fancy word they use in physics to represent lines of force. And the lines of force on a magnetic field are said to point from north to south. So if you make a north pole on a magnet, your finger would be pointing away from it, and a south pole, your index finger would be pointing towards it. Your middle finger is representative of current. And in this rule, we're using conventional current theory because this was before quantum mechanics was discovered. So Ben Franklin, whenever he came up with current theory, didn't understand what quantum mechanics was and had a 50-50 shot at getting it right, and he got it wrong. So he said positive, or current went positive to negative. The thing was, we found out what we thought was a negative charge was actually electrons, and that's what's actually moving. So even though electrons move negative to positive, and that's what gives us current, we still, in a lot of applications, describe current as flowing positive to negative. Because, again, Ben Franklin had a 50-50 shot and got it wrong, and we're all paying for it 250 years later. The last finger in your little mnemonic or visual diagram here is your thumb, and the thumb represents the force. So, it's the left-hand rule. If you have a magnetic field that points in the direction of your index finger, you run a conductor through it and pass current through that conductor in the direction of your middle finger, you will get a force trying to push that conductor in the direction of your thumb. Now, in this diagram, the current you'll be looking at will either be running into or out of your screen. The field flux will point along the screen, and the force will point along the plane of the screen, but the current will be flowing either in or out. So based on these two pictures, this one if it's flowing into the screen, this one if it's flowing out of the screen, you'll know which way the current in the armature is going. So let's look at our first scenario here, where we had the positive lead connected to the A lead, then it comes out the AA, and then we connected that to the F lead, so it goes back in and then comes back out to the negative on the FF. In this situation, the top and bottom poles of the magnet, or the top and bottom field poles in the motor would have north facing in. So the magnetic flux is going to be facing in, and the A lead is connected to the top and bottom brushes on the armature, and so the current would be flowing away in this location. This gives us a force
pointing this way, the way your thumb, or the way my thumb is in this picture. If you go to the front and rear poles, they would be south poles. Magnetic flux is pointing out. Remember, it points towards the south pole. The current has to come back somewhere to get to the AA lead, so it's coming back towards you. Force will be pointing in the same direction around the circle. So the armature will rotate in the direction of the arrow I drew, so it's going counterclockwise. Now if that looks weird, like it would go backwards away from the front, remember we have a gear set on the other end. We have the pinion and the bull gear. So this will actually drag the motor forward towards the support bearing end. So now if we go look at our second scenario where we flip that, and now we have the positive on the FF, it's going to come back out the F, go back in the AA, and the negative will be on the A. Now the top and bottom poles are south poles, so the flux points out, and you also change the direction of current. So now my middle finger is going to be pointing out of the screen. The front and rear poles are now north poles, and the current direction is pointing into the screen. Notice that my thumbs are all still pointing the same direction. So the armature is still going to rotate the same direction. Now if we look at our third scenario, we have the A lead on the positive. It comes back out the AA lead. Now it goes in the FF lead and back out to the negative on the F lead. So now your top and bottom poles are south poles instead of north poles like they were in the first scenario, and the current in the armature is now still flowing into the screen. And the front and rear poles are now north poles, and the current is still flowing out of the screen. Now look at my thumbs. They're all pointing the opposite direction. So now you get the armature to rotate clockwise, which will drive the bull gear in such a way to push the motor away from the support bearing end. This is how you get your reverse direction. You change either the armature current or the field current to change the way the armature will rotate. Now that that's out of the way, hopefully this is all making sense to you guys. I have a little rule for you to figure out which way a motor will turn. So if you write out your leads, A, AA, F, FF. This is the same order they're in if you look at the front of the motor. So if you start on a print, start from your positive and follow it along and note the first lead you come to. It will be labeled on the print. So if we go to our first scenario, that's A. Then you're going to come back out on, if you go in on an A lead, you should come out on the other A lead. So in this case, we go in on A, we're going to come back out on AA. So you're going to draw an arrow from A to AA. Then you're going to go to the third lead you come to, which in this case will be F. You're going to start on F and draw an arrow to the last lead, which you're going to come out on, which would be FF. Look at those two arrows you drew, and if they're both pointing the same direction, doesn't matter if it's left or right, but if they're both pointing the same direction, the motor will turn forward. If the arrows point in opposite directions, the motor will turn backwards. So again, if we go through our second scenario, remember, that still makes the motor turn forward. We have FF, F, and then AA, A. The arrows are pointing the opposite direction of what they were the first time, but they're still both pointing in the same direction, so the motor will go forward. Now if we go through our third scenario, we have A, AA, FF, F. These arrows are pointing at each other. They're pointing in opposite directions, so the motor would turn backwards. Hopefully that all made sense, because as long-winded as that was, we still have a little bit more to go through, because we not only use our traction motors for power, but we also have dynamic braking, and we also have another topic I want to get into a little bit, which has to do with back EMF and why transition is a thing. So now you get to listen to me try and explain the right-hand rule, but if you understood the left-hand rule, the right-hand rule should be relatively simple. So let's talk about dynamic braking a little bit.
Alright, so dynamic braking. What exactly is that? Well, in a sentence, it's a method of slowing down a train that doesn't rely on brake shoes. Brake shoes wear out and they can get too hot and stop working. So this is a different way of slowing things down. It's kind of analogous to a jake brake on a truck in the sense that we use the drivetrain to slow down the vehicle rather than the brakes. But it's not a great analogy either because it's not actually the engine. In a truck, the engine's mechanically connected to the transmission, but in a locomotive, the only thing mechanically connected to the wheels is the traction motors. So instead of using the engine, we use our traction motors. It's called dynamic braking because you have to be moving for it to work. It won't hold you stopped. A friction brake, like your air brakes, will hold you stopped even if you're not, it will hold you in place. A dynamic brake does not do that. You have to be moving for it to actually do anything. A basic overview of how dynamic braking works is we alter the connections to the traction motors in order to turn them from motors into generators, and the created electricity is dissipated across resistor grids on top of the locomotive. The energy required to generate that electricity comes from the kinetic energy of the train, and so this ends up slowing us down. Also, before we get into a little more detailed explanation, fun fact for you, SD40s or SD40-2s will actually create more horsepower in dynamic braking than they do in motoring. Make about 3,000 horsepower in motoring and not quite 3,400 horsepower during dynamic braking. So there's a little fun fact for you. Anyway, on to the actual explanation of how this works. So, just like Fleming had a left-hand rule that applies to motors, he also has a right-hand rule that applies to generators. And the nice thing about the right-hand rule is, you make the same exact pose as you did with the left-hand rule, and the fingers actually represent the same thing. Your index finger still represents field flux, your middle finger still represents current, and your thumb still represents force. However, as mentioned, the right-hand rule applies to generators instead of motors. Basically, what the right-hand rule boils down to is if you have a conductor moved in the direction of your thumb through a magnetic field that points in the direction of your index finger, the current will be induced in that conductor that will flow in the direction of your middle finger. So if we go back to our little motor diagram, this is the exact same diagram as our sample 1 from earlier. The positive on A, etc., etc., except this time the positive is actually on F and the negative is on FF. We're just going through the fields and then spinning the armature mechanically. We're also only going to be focusing on the top pole because I'm lazy as usual. I just am trying to save myself time and my computer some render time. So the locomotive is already moving forward in this situation, so the armature will be turning counterclockwise. Remember, we have a bowl gear on the opposite side. The flux is going to be pointing in still because the current flowing through the fields is still flowing in the same direction. F to FF is just not going through the armature first. So the flux is going to point in or down at this point, and the armature is turning counterclockwise, so my thumb's going to point left. And that leaves my middle finger pointing out of the screen at you. So this will turn the A lead, which is connected to the top brush on the armature, will turn that lead positive. So the A is still positive and the AA is still negative, but you got to keep in mind that now we're talking about induced current rather than demanded current. So the induced current is actually flowing in the opposite direction compared to what it was when we were motoring. And during dynamic braking, that induced current is dissipated across the resistor grids, which will slow us down. The resistor grids convert that all to heat, and there are fans up there that blow it off the atmosphere. There's a lot more that goes into dynamic braking, but that's going to be probably several videos way down the line when we get to electrical stuff. Now hang on a second. The field current is exactly the same as in our first situation, but the induced current flows in the opposite direction. Does that happen in motoring when we're trying to move the motor? Yes it does. Enter back EMF, or backwards electromotive force. So you have a motor, and you're trying to shove current through it to make it turn. Well, as that motor starts to turn, there's a voltage induced in the armature that's opposing the current you're trying to shove through that motor.
So to kind of visualize this, you can hold out your left and right hands in the rule pose I told you about, where all your fingers are perpendicular to each other. Notice how your middle fingers are pointing at each other if your index fingers are pointing the same way. That represents your right hand now represents the back EMF. And the faster the motor is spinning and the stronger the field current, the greater that back EMF. So in practice, this means that the faster the locomotive is moving and the harder it's trying to pull, pulling harder means drawing more current, the more voltage you need to shove through that motor in order to overcome the back EMF that it's creating. And in practice, the voltage should just keep climbing and climbing and climbing, but we have a certain limit where the insulation on our equipment will fail, and we want to stay within that for, safety purposes. So this is why transition is a thing. In a sentence, what transition is changing the connections to or around the traction motors in order to deal with the back EMF that's created by the rotating armatures. It's important to note that not all locomotives have a transition process. For example, a GP newer than a GP40 and an SD newer than an SD60, I believe, will not have a transition process. They just connect the motors to the generator and away they go. Older locomotives, we have GP35s that are like this, and even some older SD40s and SD45s use field shunting resistors, which I won't really talk about those much other than what they are is they're connected in parallel with the motor field so that some of the current can go around the motor field, which reduces the field strength and allows you to continue accelerating because reducing the field strength reduces the back EMF. This series isn't about those locomotives, however. This series is about SD40-2s, and -2s have only a single transition step, and that step is series parallel to full parallel. Remember in my cab tour video where I said we have S and P contactors, S for series, P for parallel? This is what that refers to. So a super basic overview of it is the locomotive will start in series parallel to have the number of paths for current. You only have to feed 3 paths instead of 6. Now as you speed up, the voltage drop across those traction motors is going to increase. And once you reach a certain speed, usually it's right around 23 miles an hour, the connections to the traction motors are altered from series parallel to full parallel to reduce the voltage drop. Now you only have to shove enough voltage to go through one motor instead of going through 2. And at this point, you're limited by your horsepower that you can produce with the diesel engine rather than how much current can you run through things without melting them. That's a super simplified explanation of transition. Transition and the transition control module, which is one of the modules in the electrical cabinet, that'll probably be its own video, if not more than one video down the road. But for now, that's a pretty simplified look at how a traction motor works, as well as how it works in dynamic braking and why transition is a thing. So now let's look at a super simplified print to see how this looks on an actual schematic.
Alright, so what you're looking at here is a simplified print. Simplified because we're only focusing on one series pair and there's a bunch of other circuits that I'm not worried about right now. An actual locomotive would have 3 series pairs and they just would be different motors. The one shown is 1 and 4, there's a 2 and 5, and a 3 and 6. I also want to mention before we get started that prints are shown with no power. Any magnetic contactors, any relays, anything like that is going to be shown dropped out. That doesn't necessarily mean everything will be shown open because there are such a thing as normally closed contacts. Now, speaking of stuff being dropped out, transfer switches don't really drop out or pick up. The whole point of them is they get to whichever direction they're supposed to be in and then they lock in and stay put. This is one of the big advantages of them over magnetic contactors because there's nothing to fail that would cause it to drop out and burn up. But as such, they have to be shown in a certain position anyway, and the RVs are shown in forward, and the MBs are shown in motoring. So the first thing I want to go through is what it takes to get one of these to move. It'll go through transition, and then we'll talk about how we change direction. If you want, you can follow along with the AAAFFF rule to figure out traction motor direction I told you about earlier. So starting out, we're going to start at the main. This is where all our current comes from, and this is where it needs to be going back to. So we're going to start at the main. It's going to go out to the positive bus. And from the positive bus, it's going to go to one side of the RV1 transfer switch. In forward, the RV1 is going to send the current through a bus bar, which a bus bar is represented by an open shape rather than a solid line. Solid lines are normal cables. A bus bar is a giant metal bar. If you look in my switchgear video or my cab tour video, you can see some bus bars on top of all the transfer switches. That's all a bus bar is, and it's represented with an open shape like this. So, in forward, RV1 sends the current through a bus bar to the FF1 lead, and it'll go through the motor fields. It will then come out of F1 through another bus bar, and then onward to MB1. Since we're in motoring, MB1 is going to be in motoring position, and that'll allow the current to proceed to the motor armature through AA1. After exiting the armature, it will go through A1 and then arrive at another bus bar. Assuming we're starting from a stop, S14 will be picked up, which will send that current to another bus bar and then onward to AA4. Current will then flow through traction motor 4 armature, out A4, and into MB4, which is again in motoring. And then that will go on to RV4, and in forward, RV4 will send that current to F4 through another bus bar. We'll then go through traction motor 4 fields, out FF4, and through another bus bar to the other side of RV4. That will then send the current back to the main's negative bus, and then go back to the main. As we pick up speed, the increasing voltage drop across the two traction motor armatures will eventually cause the locomotive's transition control system to make forward transition. When that happens, S14 will drop out and P1 and P4 will pick up. Now, the current will flow from the positive bus through the fields and armature of traction motor 1 and then through P1 to the negative bus. And it'll also flow from the positive bus through P4, and then the armature and fields of traction motor 4, and on to the negative bus. If we stop and change direction, the RVs will move to the opposite set of contacts. And so now, if we go through RV1, we will then send the current to the fields through F1 instead of FF1, and then out of FF1 instead of F1. So now the bus bars are ignored, and RV4 would do the opposite of this. It'll go to FF4 instead of F4. If you're using the rule from earlier, these will change the direction of the arrows between F and FF for both motors and thus change their directions. When we go to set up and dynamic braking, the MBs are then moved to the braking position, and S14 and B are going to be picked up. There is no transition step during dynamic braking. It is always in series. So now, main generator current, which is what we're using to excite the fields, will flow through the fields of traction motor 1, through the closed B contactor, and then through the fields of traction motor 4, and then back to the main. On an actual locomotive, this circuit would include all of the traction motor fields, whether that be 4 or 6. And then with the MB transfer switches in braking, the current will flow from traction motor 1 armature out AA1 to MB1. MB1 being in braking position will then send it to grid A, and it'll go through grid A to grid B, and through grid B back to MB4, again, which is going to be in braking position. From MB4, it'll flow through A4, traction motor 4 armature, out AA4 to S14, and then onwards to A1, and then back to the traction motor 1 armature. So during dynamic braking, fields are connected in series with the main, and the armatures are connected in series with grids. Some locomotives have all the grids and motors in one circuit. It'd be armature, armature, grid, grid, armature, armature, grid, grid, and so on. Some have them in 2, or you'll have 4 in one circuit and 2 motors in another. Others will have them in series parallel, just like, in motoring, we have 3 series parallel, we have 3 parallel series paths. They'll be set up the same way. 3 series parallel paths for the traction motor armatures.
So hopefully that all made sense. I know I've thrown a lot of information at you, and I'm not done yet. Having been through all that, why do these old locomotives use DC traction motors instead of AC traction motors, especially considering more modern locomotives use AC motors? Well, it really comes down to technology and, in later years, the cost. Now, you might be thinking, remembering from earlier, I mentioned that our main generator isn't really a generator, it's an alternator. And alternators make AC current, right? Not necessarily. You can make a DC alternator, but it puts out AC current and we rectify it to DC for the motors. Why don't we just use that AC current for AC traction motors? Well, it gets complicated. Big advantage of DC motors is that unlike AC motors, they don't have a specific speed where they work the best. As a DC motor speeds up, all that changes is the voltage required to overcome the back EMF from the armature. AC motors, on the other hand, are designed to work with a specific amount of slip, which is the difference between the speed of the RMF, rotating magnetic field, and the speed of the motor. The speed of the RMF is determined by the frequency of the AC current you're putting in, and the frequency of that is determined by, if we were to just directly connect the AC output from our main to the traction motors, that frequency would be determined by the speed of the engine. And so it would go up in steps with our throttle notches. And also, as we go up in our throttle notches, we're asking the engine to produce more power, not just go faster. And that doesn't bode super well for powering AC traction motors, because what if you want a lot of power at a really low speed or very little power at a very high speed? Well, that's, your throttle notches aren't going to work that great for you in that situation then, because those AC motors would require a very smooth increase, and, your throttle notches are going to go in steps, and on top of the whole power versus speed issue, it's just a complicated system. So how do these modern locomotives with AC traction work? Well, I'm going to pull a bit of heresy for someone trying to be educational and talk about something I've never dealt with, but hopefully this will get the concept across. And if someone watching this actually has experience with AC traction, feel free to add anything to me or correct me. So a super simple overview of AC traction is this. You have the main alternator output, which is going to be rectified to DC current and then sent to the inverters. The inverters are then going to take that DC current and invert it back to three-phase AC and send that to the traction motors. Now, the frequency of that AC current is going to be determined based on throttle position and the measured speed of the axle. And that can either be the axle directly through an axle alternator, or it can be a traction motor speed probe. Either which way, it knows how fast the axle is spinning, so it knows what frequency of AC current it needs to send to the motor. Those inverters have to be able to handle a bunch of current, and when we're talking about, high capacity solid state components, those usually get pretty expensive, and that's, hence the big cost issue for a lot of these older locomotives. That having been said, AC traction motors are pretty much bulletproof compared to DC motors. I heard a story from a guy who used to work for NS. Basically what he told me was they figured out that AC traction motors, the motors are not the weak point. The weak point is the inverters. You will melt and burn up the inverter in the aux cab before the motor even knows what's going on. The guy told me that there was a demonstration that they did with the AC traction motors where they just, overloaded the heck out of them with a cold drag, drug it up a grade until they stalled, and then they let it sit there with the throttle wide open, tied a bunch of stuff down so it wouldn't roll away, and then they went to lunch. When they came back, everything's still sitting there loading, eighth notch, wide open, sitting there at stall for like an hour, and everything was fine. So to put all that information in a sentence, we use DC traction on these older locomotives because for AC to work efficiently requires a more complex system, and the inverters for that system are expensive. So it mostly just Comes down to cost, like I said. Whew. Okay, that was a lot of freaking information. Now before we get out of here, I mentioned a couple catastrophic failures, and I also mentioned earlier, I'd mentioned what a flashover is. I haven't forgot. That's what's coming up next.
Alright, so I said at the beginning of the video I'd mention a couple stories I've seen for some catastrophic combo related failures, so that's what these are. The first one I'm going to tell you has to do with a flash motor. First time I'd ever, actually the first and only time I've ever seen one. Crew reported as they brought power up to the dock that the locomotive they were leading out of had started wheel slipping while they were pulling into the yard, and then it wasn't loading like it should have been. Knowing the power that they had, we assumed it was an issue with a positive traction control system. Bad axle alternators almost always the cause of wheel slip on those. We'd been having issues with a bunch of them. We were getting the kinks ironed out. So we assumed it was that. Upon getting it up to the dock and actually moving it around trying to diagnose it, we found out that the wheel slip issue was actually coming from the lead locomotive, not from one with traction control. So the issue must have been a motor or something like that because the wheel set wasn't actually sliding. So we then put it on a pit where you could get underneath it and look around. We used a multimeter to check for an open motor, and we ended up finding an open armature. I don't remember for the life of me which motor it was. I think it was number 2 or number 5. I think it was in the middle of the truck, but I'm not 100% sure by any stretch. Having found a bad motor, we now know what leads we need to drop in order to check it. So shut everything down, go down underneath, drop the leads we need, and then we shot it with a megometer, and the armature shot open. It showed excessively high resistance. It should, under normal circumstances, show a dead ground. Having shot the armature and found out, oh yeah, it's open, we opened the traction motor cover, and, well, I saw this. If you ever wondered what a flash traction motor looks like, it's this. Everything gets melted. The commutator, the brush holders, the brushes, brushed leads, cables, all kinds of stuff gets melted during a flashover. So what exactly causes a flashover anyway? Well, there's different potential specific causes. Over voltage, you could have commutator or brush issues. Brush dust can cause it. Just dirty cooling air can cause it because of the dust in the cooling air. Bunch of stuff. A flashover happens when the voltage applied to a traction motor is high enough to begin to establish an arc, from usually the brush holder to the commutator or something similar. As the arc is established, the resistance that's needed to get across that air gap drops. Ionized air has a lower resistance than non-ionized air. So as the arc is established, you need less voltage to be applied in order to sustain it. That drop in voltage means that for the same amount of power being put in, the amperage will rise dramatically. A huge increase in amperage will cause a lot of heat to build up very, very quickly. This effect is compounded by the fact that as the voltage drops, now less current is going to go through the other motors, and more of the current is going to go through the one that's currently blowing itself apart. And the end result is you can get a very high amount of current, and that melts a lot of stuff, and it's usually a very burned up commutator, brushes, and brush holders, and at the end of it all, the motor's just junk and needs to be replaced. So, yeah, that's a neat little story about a flashed over traction motor. I think I've seen this happen twice, and it was the same engine, and it came back like 3 months later with another burn-up traction motor. So that was one catastrophic failure, and also my quick little conversation about what a flashover is. I also got another one for you. This story happened on a relatively calm day. I was like fresh out of the apprenticeship. It was a Saturday. There's no one in the shop. We're just out there by ourselves. And I get a call from the chief dispatcher. He's like, hey, can you go to the yard and look at a locomotive? And I was like, yeah, sure. What's wrong with it? And I asked, so, I knew what tools I needed to bring. And he answered, they said the number 2 axle is jumping. He said, jumping. And he's like, yeah, I don't know what that means either. Can you just go look at it? And I was like, yeah, we'll go down there. So we Again, I'm fresh out of my apprenticeship. I've never heard of anything like this. I haven't seen anything since this happened either. But we grabbed some basic tools and then head down to the yard where they said this engine was waiting on us. We throw our blue flag on it and everything, and then we start looking around for any external issues we can see with the motor. We're checking the nose suspension, we're checking the gear case, we're checking the wheels for flat spots, we're checking for any obvious defects on the axle or something weird in the journal boxes. Anything that looks wrong on the outside. Couldn't find anything. At this point, the guy driving it was in remote at the time. He offered, hey, if you pull that blue flag and everything off, I'll move it and I'll show you exactly what it's doing. So we did, and he revs everything up and takes off with a cut of cars. That locomotive made it about 8 feet. And you heard a nice loud clunk, and the number 2 wheel started sliding. It then proceeded to physically lift the wheel about 5 or 6 inches off of the rail. I've never seen anything like it. But it picks that wheel set up about 5 or 6 inches, and you hear another loud clunk, and the axle immediately slammed back down to the rail. And then it kept rolling. It made it another 8 feet or so, and then again you heard another loud clunk. The axle picks up 5 or 6 inches, another clunk, and then it slams back down. At that point, the guy driving it stopped it. And we were like, that's something, internal, the gear case failed. That's not something, you need to swap this locomotive out for a different one. There's another one up at the dock you can take, but this isn't, you can't cut the motor out. That won't really fix your issue because something in the gear case completely came apart. So they said, all right, they left their cut of cars and then went and used another locomotive to finish up their switching and then brought us the junk one. We took it over to the shop for the drop table. Now, this happened on the weekend, and the next day I came in, I managed to find this wheel set laying around. Yeah, get a load of that. The bow gear failed and lost a bunch of teeth in the time it took for them to be like, hey, something's broke down here, and then us to go look at it, and then the time it took to get it up there, it sheared just a bunch of teeth off the bow gear. I tried to find the pinion and couldn't, so you'll just have to settle for the picture of the bowl gear. But yeah, this was the first and only time I've ever seen a gear case failure on a locomotive. Not sure exactly what caused it. I don't know if they were trying to apply a lot of power and then, it wheel slipped and then caught on a joint or a frog or something random, and that sudden impulse was enough to break a gear tooth off. I don't know. And like I said, I never did find the pinion. I have no idea what that looks like. Yeah, there's 2 catastrophic combo-related failures I've seen in my short career. Thank you guys for listening to me ramble about traction motors for probably an hour and a half, or at least close to an hour and a half. So, thanks for watching, and have a nice day, all of you.